Yeah, and yeah, I think as everyone just heard, we're going to record this. Okay, yeah. So this is going to be kind of an introduction on the to this course. So basically, just a sort of a, a, a run through of the agenda a little bit, and then we'll kind of just show you some of the things that we'll talk about. And obviously, when you do the course, there's going to be a lot more than just some of the examples. But I just want to give you an idea of the kind of things that we would kind of cover in this course. Okay. Yep. And I won't go through this again. It was a very good introduction, basically covering the same thing. But I've been teaching these kind of courses for about the last 10 years now. So I've done that. I think it's well over 100 of these courses. I think I actually counted once, and it's quite scary when you do that. Okay. Um, yeah. So what we want to try and do with our seismic data is we want to be able to get some idea of what's going on in the reservoir. Okay. And so what I want to try and talk about, or in this course and in this webinar, is how do we get information about the reservoir, and focusing on seismic data. There's other things we can do, obviously, with geology and other techniques, but concentrating on seismic. And when we've got a reservoir, and this is kind of an example of from one of these open data sets. This is F3, I think it's from Holland somewhere, offshore Holland. And they've got a porosity cube here. So in my reservoir, what am I interested in? Well, I'm interested in the structure. Okay, so where is the reservoir? How deep is it? What kind of trap is it? Are there faults? So I want to sort of map out the closures and the volumetrics, and that's the sort of not the old-fashioned, but that's the workflow that at least up until the sort of 90s, that was pretty much what we could do. So we could try and map the reservoir, we could look for faults, we could try and map out pinch outs. The seismic data has got a lot better than it has. We've gone from 2D data to 3D data to migrated data to PSTM and now to PSDM. So the images of the structure and the depths and the resolution that we have, where we can see, where exactly are the faults, what's exactly is the structure, has got a lot better. So we get quite a good picture of the reservoir a lot of places. Okay. And one thing just to mention, is that I know a lot of you listening work in parts of the world where you have onshore seismic. I'm actually sitting in Stavanger right now, in the North Sea, where it's offshore seismic, where things are a lot easier. And I do appreciate that, that a lot of the nice examples that I'm showing are from offshore data, and it's not quite so easy to do this onshore. You've got a lot more challenges getting good data, but generally the seismic data is improved. So we want to get an idea of where the top of the reservoir is, where's the bottom of the reservoir, what's the volume in there. We might want to know what the seal looks. Well, we do want to know what the seal looks like. So what's going on above the reservoir. And for those of you who have been kind of following the progression with CCS, carbon storage, and that kind of stuff, one of the things that is happening is that we have to make a better picture of the overburden. Okay, so the European Union, for example, is going to require that there be 2 seals for any CCS structure. And what that means is that we can't just map the just above the reservoir. We're going to have to map all the way to the surface. So that's a change that might be coming, and people working so not necessarily working in oil and gas, but in other parts of geophysics, other applications, we have to look at more at the overburden. So what's going on above the reservoir? We can look at things like stratigraphy. Okay, so I can see the shape, and I can look at the relationship between the reflectors. So on this example here, it's a little bit hard to see, but there's some prograding beds here, and we know from the geology that might be sand. Okay, and this is an old idea from the 70s or before. Vale and Mitchum, very famous paper about looking at sequence stratigraphy. We can still apply that. So we can try and look at the shape of the reflectors and get an idea of what's going on inside the reservoir. And something that's very important is faults and fractures. And again, coming back to the sort of CCS um, world or the green transition. Um, One thing is storage. The other thing is that in a lot of countries, um, they are not going to issue new exploration licenses. So I live in Denmark, and the Danish government is not going to issue new exploration licenses. Okay, so what that means is that there's going to be a lot of effort to try and maximize the production from the existing fields. Okay, so we're going to try and make sure that we know exactly what's going on in the reservoir. We get absolutely everything out because we may not be allowed to drill new wells in the future. Okay, so then knowing exactly where the faults are, where the fractures are, exactly how the reservoir is going to be produced is very important. Okay, and the more horizontal wells that are drilled on reservoirs, the more obvious it is that there's a lot more fractures in there than people have mapped. And so they make a big difference. So I need to sort of effectivize my production. Okay, um, we can use the seismic to look for fluids. Okay, so you probably may have heard of bright spots and flat spots and things like that. So direct hydrocarbon indicators. Um, so we can use them to try and identify areas of interest before we start drilling, but also we can use the seismic to try and estimate fluids. So we can do things like inversion, um, and we can take sort of what was deterministic inversion, which is sort of a slightly older technology, and what people are doing more recently is doing things like rock physics inversion. So we can get petrophysical parameters. Okay, so porosity, saturation, clay volume are all things that we can try and invert for. Okay, and one of the newer applications is what we used to do is calculate things like acoustic impedance and VPVS and density, and then use them to calculate the petrophysical parameters. What a lot of the latest software is doing is actually inverting for the petrophysical parameters directly, so we get a better answer. So these are all things that potentially the seismic can do for us. Okay, so it's not just finding the structure; we can maybe get some idea of the parameters. And in behind all of this, it's obligatory. You can't not have a presentation that doesn't mention artificial intelligence. There are a lot of efforts being put in to try and automate a lot of these processes. Okay, so can I automate my structural picking? Can I automate my fault picking? Can I automate the process? Can I identify what the lithologies are automatically? So I'll try and I'm not an expert in AI, but where there are AI possibilities, I'm going to try and highlight that because it is the big topic right now in basically everything. How can we use artificial intelligence to help? Okay, so I've kind of split the course up into sort of 5 sections. So the first section is some introduction, so a little bit of some of the terminology to make sure that everyone understands exactly what we're talking about. Some basic things that you need to sort of think about, because not everyone's a seismic expert when that they're signing up for these courses. Then talk a little bit about correlating with the geology. So how do we do that? We have wells. They are very useful for finding out because the seismic is just basically wiggles. So what do we do with the wiggles? Which wiggle belongs to which piece of geology? So we can try and match that up. So that's the well correlation is a very important step. And then talking a little bit about focusing. So one thing we're always trying to do with any kind of sort of survey or any kind of work that we're doing is trying to minimize the amount of work we have to do. Okay, so if I've got a very big survey, I don't want to have to go through every single square kilometer looking for prospects. Maybe I can focus in. So we'll kind of talk about things we can do to try and shortcut the process a little bit. So looking for DHIs, how do I look at the bigger picture and then decide where to work? Sometimes sometimes it's just a survey. You work on the whole survey, but you can also get 10,000 square kilometers, and where do you start? Okay, and then some some tips about seismic horizon interpretation. So basically, where's the top of my reservoir? How thick is the reservoir? Are there pinch outs? And I mentioned AI already. There's a lot of work being done trying to automate this because for those of you who've done seismic interpretation, it can take a very long time. Okay, sometimes it's easy, wow, but a lot of times it can be very, very time consuming. So can I speed up that process so I don't have to spend months and months and months trying to pick wiggles on my screen? Um, so that's the sort of first day. Second day, we're going to kind of talk a little bit about faults. So we have the horizons, which are going to give us the depths to our prospect. But then our prospect might be delineated by faults. Okay, so where are the faults, and how can I speed up the interpretation of the faults? So where's the edge of the reservoir? Are the faults going to be sealing? Things like that. And then we'll talk about spectral decomposition in thin layers. So one of the things that has become made life more difficult for people working in the oil business is that if you go back 70 years, 50 years ago, um, the prospects were big. They found it with very old seismic because they had these huge structures and hundreds of meters of reservoir. Um, we There are very few of those left. I'm not going to say there's no reservoirs, but most basins have been explored, and we're looking at thinner and thinner reservoirs. So we start running into some physics, and that's basically that our seismic has limited resolution. So things like identifying thin layers, looking for channels, so whole sort of spectral decomposition. Can I look at different frequencies? And then the effects of tuning. So we'll talk about that. Okay. And then how do we map channels? This is something that is difficult to do on 2D, but it's relatively easy to do on time slices. And it's even better to start picking things like horizon slices that follow the geology. So we'll talk about that. And then I've kind of put depth conversion in here. Okay. And one of the things that we need to sort of worry about a little bit, I'll mention it a little bit later, is our drillers are drilling in depth. Okay. A lot of our things we want to do with seismic, we're doing in time, and we need to have a conversion. And that's one of the things we do with our well correlation. But also, it's something we need to bring everything back to depth. And that's also going to affect the volumetrics. Okay, so making sure that you use the right velocities and do this properly. And this is also somewhere where we can start introducing uncertainties. Okay, so I'm picking a horizon, and I've got some wiggles, and I pick that wiggle. Okay, and I've got a horizon, and that's one value. Um, can I start getting some idea of what the variation is on that? Because I think that's a very important in terms of risking your reservoir or your exploration reservoir. So we'll talk about faults and then getting the depths and everything correct. The third part is internal structure. So how can I work out what's going on inside the reservoir? Okay. And so this sort of first 2 days were things that were are more typical sort of seismic interpretation. I think get to day 3, we're kind of getting into sort of quantitative interpretation. Okay, so we'll talk about seismic attributes. We'll talk about seismic facies analysis. We'll talk about thicknesses and stuff like that. We mentioned that already a little bit, but also how do I calculate thicknesses? And then we'll kind of look at the sort of supervised and unsupervised classification and AI. So how can I take my seismic and get properties, so maybe porosity, maybe some idea of sand or shale, from my seismic data. Okay. And it's not so easy sometimes to do it just by inspection. You might be lucky and you can get inspect. You can say, well, okay, that attribute sand, great. A lot of times it doesn't work like that. And so what we can try and do is use these, use the supervised and unsupervised classifications. And this is where the AI comes in. So can I turn my seismic data into sand and shale, which is what the geologist would be very interested in finding out, rather than a bunch of wiggles on a screen. So that's the sort of internal structure. And then day 4, we'll kind of talk about the fluids. And this is where we get to sort of AVO or AVA. Okay. So our post-stack volume does see some effects due to fluids. But typically what we need to do is get gathers and look at the amplitude variation with offset. Okay. And related to that are things like fractures. And so that's something we'll also look at. So AVO is pre-stack. And then in pre-stack, we also can do things like a pre-stack seismic conversion. Okay, so we can get properties like VPVS, so which is our Poisson's ratio, which should, all things being should equal will tell us about the fluid content in our reservoir. So that's day 4, and then day 5 is kind of bringing it all together and getting a map out of the petrophysical parameters. Okay, so things like porosity and lithologies, and we'll talk about stochastic inversion and uncertainty, how we put in some variation in there. So can we imagine that we got higher frequencies than we really have, and so what would the reservoir look like? And I can make multiple models, and from those multiple models get an idea of what the range of values could be. So that then I can then plug that into my reservoir modeling. We'll talk about the rock physics inversion, which kind of incorporates some of these features. And then the final part, I won't spend too much time about it, but I'll just kind of highlight some of the things about building geological models. So the final results from my reservoir characterization should hopefully be some data set that the modelers can use to build a better geological model. Okay, and related to this is things like history matching. Okay, so if I'm building a reservoir model and I've got data, time-lapse data, does that match the production? And if it doesn't match the production, what's going on? Okay, so can I build a better geological model using the seismic data? So this would be sort of time-lapse. Okay, so just some sort of topics that are kind of of interest here. And one thing that's very important, and I mentioned this already. I apologize to the people who are working in there with land data where it's a little bit more difficult to do this. We have to have seismic that's representative of the geology. Okay, and that's easy to say, not necessarily quite as easy to do sometimes. Okay, so you can see on the left we've got a couple of different time slices here, and you can see these vertical lines are artifacts of the acquisition. Okay, and you see they get less as we get deeper, but basically we've got a line spacing, and we're getting changes in amplitude. Okay, so if I then try and interpret that, I might be able to kind of, it's certainly going to make my auto tracking harder, but I might be able to interpret my way through this. Okay, because I can kind of see it's the same reflector. It's not a problem. But if I start doing anything kind of automatic or do inversion, those vertical stripes are going to look like a geology. And you do get geology that looks like that, So if you've got a fan, if you've got some kind of slope with a bunch of canyons that happen to be sort of north-south and following the edge of your survey, you could get something that looks like geology. So I can't eliminate it. I can see it's following inline cross lines, so maybe I have a suspicion. But we need to make sure that everything looks okay. And then the other problem, is coherent noise is a problem, but also things like, does my seismic match my true amplitudes? And if it doesn't, then I've got a problem. Okay, so here's an example some gathers. So this is so the near traces on the left are 0 degrees, and then the far ones I think are 50 degrees. I can't remember exactly. I think it's 5 degrees each of these. And if I do a forward modeling exercise with my well, I get 1 AVO. You can see here, and then on the right there's the gathers that I've got for this survey. Okay, and the problem is that you see they don't quite match. Okay, there's a little bit of a time difference, and you can see there's an amplitude difference. So I need to try and make sure that my seismic's processed. And I think for data you get now, so if you pay for a survey in 2025, there's a very good chance that they'll get this right. They know what they're supposed to be doing. If I get some seismic data from 2005 that hasn't been reprocessed, I'm not going to be sure if it's going to match or not. Okay, so this could be a problem. So I need to kind of need to do something about that, or check that. Okay. So that's one thing that's very important is the true amplitude nature of the data. Another thing we have to worry about is depth and time. And here's an example from some data from Equinor. This is Volva, which is actually this data is free for people to download online. I think you just have to register, and you can download this. And you can see that the left-hand side is depth data, so PSDM depth, and then the right-hand side is the data that's been is the same data set but converted back to time. So we've used the velocities that have been used for the PSDM, and we've converted the depths and converted it back to time. And you can see that there's a difference. Okay, the depth data is stretched. You can also see that the shape of the seismic is changed. And this causes us some problems when we start playing around with inversion and with attributes, because a lot of our theory behind a lot of the processes that we apply assumes that the wavelet is the same all the way up and down. Okay, and when it's not, as you can see here, we've got a problem. So this is something that we're kind of in a transition. So a lot of our data now is PSDM depth, and the PSDM data is better imaged than the PSTM data. But we still have to convert things back to time. So you have to be a little bit careful. I've had at least one experience where we had some depth data that was being interpreted in depth. We had some time data that we thought matched, and we had a velocity that matched the two. It turned out that there was a problem, and we had to readjust everything so that the work that had been done in time and the work that had been done in depth matched up. So just be aware of this. It's something that I think maybe in 5 or 10 years this will be fixed. We'll do everything in depth but behind the scenes it will be converted to time. But right now we have to worry about it. Yeah, so we need to use the velocities, and this is somewhere we've got better velocities now than we used to do. Okay, so these velocities are going to be part of the processing, but we can also try and use these for depth conversion. Okay, but one thing just to mention is that if I go in and check all the times and the depths on my PSDM data, it still doesn't quite match the wells. Okay, there's still actually a shift. So we still have to do some corrections. Okay. Yeah, so I mentioned picking horizons. So that's one thing that we want to do. So, how do I do this? Do I pick it manually or do I do auto tracking? Can I get AI to do it? And there are certainly a lot of efforts being done on doing that. Can I see anything? So I've got a reservoir that's 5 meters thick. I'm probably not going to be able to see that. Okay, because it's too thin. So I need to have a survey that's been designed that can maybe resolve that. It's probably not going to happen. You're not going to be able to get the frequencies. Okay, can I pick the top and the bottom of the reservoir? If not, what's going on? Is there tuning? Can I see amplitude variations? Is it there? And so if there's tuning, can I use that tuning to try and infer what's going on? So it's not just going in and clicking and going, there's the top, there's the bottom. There's a lot of things that we can maybe do before we pick our reservoir. Okay. Faults. Yeah, this is something that's it always seems to be very time consuming. If you're lucky, you can do one click and get a whole horizon. If you work in the North Sea, the top of the chalk, usually you can oftentimes just do one click and it basically covers the whole of your survey. With faults, it always seems to be a lot of hard work, but they are very important. They're going to delineate your trap, and then smaller features are going to be important when you're trying to work out, how's this reservoir going to be produced. And so, how can we speed up the fault picking? Do I need to go in and pick every fault, or can I kind of use some kind of auto tracking and speed everything up? Okay, and then can I? I've done the interpretation here on the seismic data. Can I make some attributes? So some of you might have heard of ant tracking. There are a bunch of other attributes. So instead of using the seismic, I can look at, say, the variance or the coherence in the seismic. And every time I've got a fault, I'll get a change in the coherence or a change in the variance, which is basically 1 minus the coherence. And so can I use that? So can I map on that rather than mapping on my seismic data? And then once I've got a data set that I think is nice, can I then automatically extract faults? Okay, so can I go in there and instead of having to go in and pick every one of these faults myself, can I get some AI to do that for me? And here's an example from I think it's a leading edge paper where they've done that. So they've done the picking on not on the seismic amplitude data. They've done it on I think it's ant tracking. They did it on, but they've done and then they've enhanced the data and then done the fault picking. So we'll look at that. So if I've got a fault, I'll get a break. If I've got a fracture, and where a big fracture becomes a small fault, I'm not quite sure. They've got a cartoon here. Oops, excuse me. Not what I wanted to do yet. Yeah, so they got a picture here, some cartoons here that I borrowed from this paper. So here's my fault, and it shows up on coherence. If I've got a small offset, I don't get any coherence perhaps. But what I can do is maybe look at the curvature. So this is an example of doing that. Okay, so I don't get a jump, I get a little wiggle. Okay, and I get a curvature one way and then the curvature the other way. So I get this K1 and K2, and they're opposite curvatures. You see on the left here, there's a little cartoon sort of showing you how it happens. So I've got a curvature one way, and then I got a positive curvature and a negative curvature. And then what they've shown here is I can look at these pairs, and then they had the idea of calculating the third derivative. So I've got the slope, and then I'm going to look at the dip, and then the curvature is the second derivative, and then the third derivative is this what they call aberrancy. So now that's an attribute that will sit on the fracture itself. Okay, and if I'm mapping in CCS, this is an example from CCS. Maybe this is something I'm going to be useful. And also it's going to be useful for oil exploration as well, knowing where the fractures might be. And this is an example. I think it's if I remember, it's some data from onshore in the United States. I think I won't. I think it might be Texas, but don't sue me if that's not correct. And you can see here that basically it's a little bit too much maybe, but the black is coherence. Okay, and so in this example, you can see in the sort of top layer above the sort of purple, you can see a lot of coherence changes. So there's a bunch of fractures or faults up there. In the layer below, there's not so much going on. Okay, but if they calculate the curvatures, you can see that there's actually quite a lot of things going on. Okay, and so we're by looking at the curvatures, we can actually identify a lot of smaller features that we can't see in the curve in the coherence. And this is the kind of thing that we could try and use to improve our fracture modeling or fracture picking. Okay. So yeah, fractures are important. And faults are important. They're the edges of the reservoir a lot of times. We can also try and map the reservoir by looking at the seismic character. Okay, so can I find a channel? So maybe I can find the top of the channel, but maybe I'll have some kind of character change. Okay, so this is a couple of examples from a paper, and they've got different geologies here, and hopefully you can see that there's a change in the seismic character. Okay, so this kind of gravity slide here has got a different character from the other seismic in the profile. Okay, and this channel looks different. What else have they got? They've got a fan here, and then some other features at the bottom here. So essentially, we can see differences in the seismic character. Okay, and maybe what I can do is not just use the amplitude. I can take a bunch of other attributes and kind of make a picture. So eventually, what I'll hopefully get is a bunch of different colors that match up with different features. Okay, so so each of these sort of different seismic fascies, I can find some attributes that match, basically 2D attributes or texture attributes, and then I can combine them and make a model. Okay, so the red is basically in this case I can use reefs, and then the kind of cyan is in between the reefs. And in this example, this is some channels. Okay, and different parts of the channel system show up in different colors. Okay, so can I do this? And this is one of the places where I think that AI helps. Because artificial intelligence helps. I can't do 26. I can maybe handle 3 attributes. I certainly can't work out what 26 look like in 26-dimensional space. But we still need the interpreters because someone needs to work out what these things mean. Okay, so for those of you who are a little worried that your jobs might disappear because of artificial intelligence, I don't think it's going to happen that soon. We still have to work out what these different colors mean, but we can get some help making the colors. Okay. Yeah, so I can identify different kind of seismic fascies. Another thing we can do is just look at the character of the seismic. Okay, because we know that different kinds of lithologies behave in different ways. Okay, so this is the curvature again, just because it also makes some nice looking slides. But basically, if I've got something that's hard, which is like a carbonate, I get different when I put something on top. It behaves in a different way, it compacts in a different way. Okay, so maybe I can get a clue about what's going on. And I do have to be careful. I could probably make this kind of feature in another way. Okay, so with all these things, there's always maybe another way you can do this. Okay, but if I've got something that's soft, for example, a soft channel might show this kind of feature. Something that's hard is going to have an opposite curvature. So I can try and get an idea of what's going on in the reservoir from what's going on around it as well. Okay, so because where there's no sand, it compacts more than if there is sand. Okay. Yep. I can combine my data. So one thing that you may have all seen these spectral decomposition or blending, where you blend different colors. Okay, so this is some data with some channels, and what they've done is they've looked at sort of 20 hertz, 10 hertz, 20 hertz, and 30 hertz. So basically, we are looking at the amount of each of these frequencies in the data. So we've got 3 different cubes, then we combine them. And if the colors are the same, if the values are the same, we'll get white or black. Okay, so if they're all 1, we get white. If they're all 0, we get black. Okay, and you can see here on this seismic slice here, you can see there's a lot of where there's a channel, we get some reflectivity. Where there's no channel, you see there's not really much going on. There's not a lot of reflectivity. Okay, and so that's why it shows up as black. And then you see where we got the channel, we got different colors. And if we're lucky or smart, or combination of the two, we can pick these frequencies. And so if we have some idea what the thicknesses and the velocities are, we can kind of pick the frequencies that will highlight that. So as my channel changes thickness, I'm going to see a different tuning effect at different frequencies. Okay, so it's going to go from red to blue to green. In this case, it's mostly going from blue to green. Okay, but if you look in detail, you actually get you can actually see that as we go around the bends of the channel here, the thickness changes in a way that we would expect when we see the channel. So basically, the channel should be deeper out on the edge here, and then the deep part flips over to the other side. And if you kind of look in here, you can see there's blue on the edges, and that fits with what we'd expect from a real channel. So we can use the spectral decomposition to get an idea of what's going on with sort of channels reservoirs. Okay, and then we can also try and model thicknesses. Okay, so here's an example of a wedge model. So this is some real seismic, some real well data, sorry. And what they've done is they've basically taken a real well and they've made the thickness of the interval, reservoir interval, go to 0, basically. And then in the other direction, they've made it wider. And what I can do is make a whole bunch of, basically make a synthetic seismogram. And then I can see what the effect would be. So in this case, what they've done is they've made the synthetic seismogram, and then they've calculated these isofrequency or frequency attributes, and then they've done the blend. Okay, and what they can see is that if it's thicker than their their control well, we get blue in this fan. If it's thinner, we get green. So you see that at roughly this thickness, we go from red to green on that in the bottom part of the reservoir or the bottom part of the fan, and in the top fan it goes from blue to nothing. So we can try and look in our cube and see if we can identify these kind of features. Okay, so we then have an idea what that thickness is. It's a little hard to read on the slides, but we've got an idea what the thicknesses are. So we can get an idea of how thick our sands are. So is that going to be worth exploring or drilling? Okay. Yeah. Another things we can do is we can try and use the well data, and we can use attributes. So this is just an example of a simple workflow where basically I've got a bunch of wells where I know the real thicknesses are, and what I can do is calculate a bunch of different seismic attributes, and then see if they correlate with the thicknesses. Okay, so if I've got so in this case I've got the thickness and then basically the tuning thickness. Oh, sorry. Yep. Yeah, so basically I can match the tuning thickness, and if there's a correlation, I can then use that to try and convert my attribute into a thickness map. Okay. So this kind of workflow, we need to have plenty of wells, and I think you can see that, well, there is a correlation, but yeah, maybe I shouldn't use some of these wells. But that is another way of kind of estimating thicknesses as opposed to doing this wedge modeling. Okay. But I need to have enough wells, and as I say, you can see that maybe I should be fitting some kind of curve rather than a straight line. So it's not perfect, but it might be useful. So I've got my reservoir, I've got some idea of my thickness, and then I want to know what the properties are going to be like in the reservoir. So I need to have some idea of how my reservoir might behave. Okay, so what happens when I change the porosity? Okay, and what happens if I change the V clay? What happens if I change the saturations? And so this is an example here of a bunch of real data. And then here's my P wave velocity on the vertical axis, and then my porosity on my horizontal axis. And the Royce bound is basically the softest rock you can have with the minerals in the rock. The Voigt is the hardest rock. So basically, the real rock should lie in between this softest and hardest boundary. And you can see that in this case, you have a lot of suspension. So basically, very unconsolidated rocks and you see they lie very close to this Royce boundary. But what I'm hoping for is that I've got some kind of systematic relationship. So you see, if I take the clean sandstones, like these ones up here, you can see there's a pretty nice linear relationship. Okay, so I've got a linear relationship between, in this case, the P wave velocity and the porosity, and I can use that to try and estimate porosities. So that's the kind of thing that we'd like to be able to do. We can do inversion, and we can do inversion post-stack. So that would be maybe, oops, sorry, post-stack would be maybe to get porosity. If I get this nice linear relationship, I can get an acoustic impedance cube, and that's related to the P wave velocity, and I can, probably get a porosity out of that. If I have any changes in the saturations, then then this won't work. What you'll find is I won't have one trend. I'll have two trends or several trends that I can't really get a linear relationship. So then maybe what I need to do is do pre-stack inversion. And this is an example from Denmark. And what this is showing is they did a 4D survey, a 4D analysis, and the blue is the saturation. Okay, and what we've got is a kind of we've got a rollover. It's an anticline, and I mentioned fractures earlier. You see, there's a bunch of these features in the seismic, and they weren't modeled. So when they did the original analysis, they didn't include these small faults or fractures in the reservoir model. And this is what the reservoir model predicted. Okay, so this is what the reservoir model, after I don't know how many years of production. So they're injecting water, and this is where the water is gone in the reservoir model. When they looked at the seismic data, what they could see, the inversion data, is that you could see that they were getting, basically the water was going along these fractures. Okay, and so basically the production wasn't matching. They knew that. Okay, so one of the reasons they shot the seismic data was that they were finding I think they were getting water coming out at breakthrough much earlier than they were expecting. So they knew there was something wrong with there was something wrong somewhere. And then when they did the 4D seismic, they could see that basically they hadn't included these fractures, these faults, and they were important. Okay, so basically in this case, there's a horizontal well. Okay, so these fractures are actually getting injected directly into, so the water is going down the horizontal well into the fracture and then back out the producer, which is also another horizontal well. So you need to go back and change the model and change the way that they're producing the field. Okay, so we can look at saturations. We can also use our properties. So I talked about using seismic character to identify different lithologies. We can also go in and look at the elastic properties. Okay, and then what we can do is do some Bayesian inversions. Okay, so I can not only get the lithology, I can get the probability of the lithology. So this is a very useful thing to be able to do. Okay, so now I've got some uncertainty. Okay, so I can say, look, okay, right, I only want, so if I do 90%, 80%, 70%, what does that give me in terms of the reservoir volume? Okay, and this is information that the engineers will be very interested in. Okay, yeah, so I'm nearly kind of out of time, and we're on the last slide, which is great, or the second last slide, which is great. So what we're all trying with all of this is to produce information for the geological model, or so the model that will go into the reservoir simulation. Okay, because that's kind of all the rest of this is very interesting to the geophysicists, but what the engineers want is or the geologists want help to build the geological model, because we got a lot of information between the wells that they don't have. Okay, and what we can hopefully do is produce a better model. So then when we shoot our 4D seismic, the 4D seismic matches the reservoir model. Okay, so there's no surprises. Okay, but as I said, at the start, we're moving into a time where things like CCS and governments are refusing to issue new licenses. So maximizing production is going to be important. And And then also, if I've got if this is my CO2 reservoir that or that storage facility I'm planning, I really don't want to have that kind of stuff in there that I don't know is there. Okay, I can't ignore this because this is going to make a difference to how the fluids move in the storage facility. So it's going to be very important in the future. Okay, and also I'm going to have to monitor my reservoir or my storage facility. So this is going to be the time-lapse seismic, or as one of the options. Okay, but yeah, so just to wrap up, the course would be 5 times 4-hour sessions, and then we record them, and then we'd obviously share the material with the participants. Okay, and I do have some data sets, so some of the stuff that I'm going to show, I'll be able to kind of give people some publicly available data sets so they could try out some of these things themselves. Okay, so not all these examples are public data, but for example, this some of the most of the data sets I've used here are public. So we've got some examples of sort of doing the workflow, and then we can share the data. Okay, but thank you for listening. And I guess if people have questions, I see I'm getting a message saying there's too many people logged in or something. I don't know if that's